Alright, I'm going to talk about 2.6. I'm going to chop 2.6 into two different videos because there's a lot of stuff in there. This is maybe the easier of the two, and then I'll talk about the stuff a little bit harder in the next video. So there's a bunch of different special functions they talk about in 2.6. And so it's just a wide variety of things that you should be able to handle, but lots of different types of things. So the first type is what's called a constant function. And it's called constant because the y value does not ever change. So I'm not even going to draw this. I'll cheat because they're straight lines. These first two are both straight lines. And so the dark green one, f of x equals 5 or y equals 5. Okay, literally that says the y value, no matter what, is always 5. So I go up 1, 2, 3, 4, 5, make my line. Boom. And so constant function is always horizontal lines. That's what a constant function is. Or I'll graph both of them on the same graph here. F of x equals -4, y equals -4. Both of those are ways of communicating the same constant function. And so down 1, down 2, down 3, down 4. That means the y value would be -4 like those blue equations say on the bottom. And boom, there you go. There's two different constant functions graphed on the same graph. Okay, the other type of function that is one of the special functions that's pretty easily accessible, at least compared to some of the ones we're going to do on the next page, is the identity function. And so it's called the identity function because when you plug in an x, you get the same number for y. So your x and y have the same identity. So no matter what, x is, y is the same thing. And what that picture looks like is, and you might guess, it's a straight line. And it's a straight line that is going through the origin. So the y-intercept is 0. So you can think of this as x plus 0 if you wanted to. With the slope of 1. Okay, up 1 over 1, up 1 over 1, up 1 over 1. Slope of, let's see if I can squeeze it in here, slope of 1. So there's your y equals mx plus b stuff, but you don't really ever need to actually write that. I'm just pointing out that it's a linear function. M is 1, b is 0, y equals mx plus b. Alright, you never really necessarily see it like that. There you go, that's the identity function. 45-degree angle going through the origin. Okay, so here are the two examples of more complicated special functions that you find in 2.6. The one on the left is called a step function. Okay, and you can think of a step function as just a bunch of horizontal line segments. So this is a bad example perhaps, but it kind of can look like steps. For instance, over here on the right. Okay, this is also a step function called the greatest integer functions. A step function is just a bunch of horizontal line segments. Notice you got a bunch of open, shaded circles and unshaded circles. Just like when we were talking about graphing inequalities, that we shaded in sometimes. That means the point is supposed to be there, and we didn't. That means the point isn't there. So, for example, this right here at 8, 2. This point at 8, 2 is not on the graph. So you go over 8, up 2, and there's an open circle indicating that's where that line segment ends, but that's not really a point on the graph. F of 8 oops, back up. F of 8, let me see if I can write this, is not equal to 2, it's equal to 1, 2, 3, 4, 5. This point up here, 5. So when x equals 8, y equals 5. See, f of 2, just for example, is equal to 1, 2. Okay, not up here. F of 2 is not equal to 5. That's the open circle, the not shaded in circle. So f of -2, one last example, hopefully that's enough, equals me start over. F of negative 2 is equal to this point right here, whatever this y value is, which is 7, I think. 2, 4, 6, 7. Okay? Because that's a shaded in circle. So there you go. There's a generic step function. There's no formula for it because it's just kind of crazy. It's really technically a piecewise defined function, which is what I'm going to talk about in the next video out of 2.6. Okay, so let me get rid of this stuff. Don't really need it. So the greatest integer function is a very special step function. I'm going to zoom in a bit because I'm going to be pointing to it a lot. Okay, now the greatest integer function, this is the formula. This is the symbol for the greatest integer function. And what it really is, it's a round down function. So take whatever the x is, whatever's in here, and round it down. So I'm just going to try to plot points here. Okay. So I'm not going to write anything. I'm just going to try to, so listen carefully. So 1/2. If you round 1/2 down, always. So even though you might want to round, you're taught to round up when it's at 0.5, but the point is you're always rounding down. This is the magic thing that this function does. So you always round down. So with x equals 0.5, if you round that down, you get y equals 0, and so you get that point right there. So, oops, I should make that a little bit bigger. That's why that point there is on the line. Okay. If you have 0.9, you round. If you're always rounding down, the y value you would get would be 0. Round 0.9 rounds down to 0. I know the rules say, hey, you round 0.9 up, but that's not what this is doing. It's not rounding by the normal rounding rules. It's a made-up useful function for things sometimes. We're always running down, so that's why that point, I'm going to say this right here, 0.5, 9 I should say. When you hit 1, well, what does 1 round down to? The nearest integer. Okay, 1 rounds to 1, so boom, there you go, that's why this point is here. 1.1 rounds down to 1, so you still got a point, 1.5, 1.7, all those round down to 1, so the y value is still 1 that whole time until, well, bam, you hit 2. And then what's 2? What happens at 2? Well, 2, if you round 2 down, you should get, well, you still get 2. So when x equals 2, y equals 2. Okay? The negative is the most confusing. If you have, like, let's say, negative 0.5. So negative 1/2. How do you round down negative 1/2? Well, you make it more negative. That's what it means to round down, is it makes it smaller. So sometimes students just want to knock off the fraction part and be done with it. That's not how it works. I mean, it does, actually, that is kind of how it works on the positive end. But on the negative end, it does not work like that, so it's important not to think of it that way. Negative 1/2 rounds down to negative 1. So negative 1/2, negative 0.5, boom, you go way down to negative 1. Negative 0.9, boom, you round down to negative 1. Negative 0.1, or excuse me, negative 1, you stay at negative 1. But as soon as you get beyond negative 1, say to negative 1.3, let's say, negative 1.3, you round that down to negative 2. It's always getting smaller, and so on the negative end of things, that sometimes confuses students. Okay, so negative 1.3 rounds down to negative 2, so that's why this point is right here. So with all this, that's why you get these horizontal line segments. And this is a step function. Okay, greatest integer function is a step function. It's just a very special one that comes up a lot. Okay, so I'll do one last example in this video, and it's the hardest thing on the video, so make sure to pay attention to this. You might have to watch it a couple times. But a greatest integer function with that transformation. And transformation, all that means is that the equation is changed a little bit. And when you change the equation a little bit, what that usually does is changes the picture in a little bit, in a predictable way, hopefully predictable way. So you change the equation, so it's instead of just an x in here, for instance, it's x over 2. And so that is going to actually change what the picture looks like. Okay? So what I'm going to do is I'm going to try to help you figure out what that's got to be. So let's say I'm going to just type them in as we go. Well, this is supposed to be y, of course. Okay. So what is it going to be if you plug negative 5 into this equation? So you do -5 over 2 is -2.5, and you round it down. So you round -2.5 down to -3. Okay? -4. Maybe. Alright, -4. -4 is divided by 2 to -2, and you round that down to, well, heck, it just stays at -2. Okay, you're always rounding down, but you're already at an integer. -2. Okay, -3. Okay. Round it down, divided by 2. Alright, so you get x over 2. So you get -1.5. Round it down, you get -2 again. And -2. X over 2. You get -2 over 2 is -1. It rounds to, well, -1. Okay, so you round -1 to, well, it stays at -1. -1 divided by 2 is -1/2. You round that down, it goes down back to -1. Okay? So you might be starting to think, notice what happens here. If you note, if it's just regular old greatest integer of x, these extra dots are confusing. If it's just greatest integer of x, these steps are 1 across, from 0 to 1, 1 to 2, so on. Over here, you might be starting to notice the steps appear to be wider. You're at -2 for, well, a couple of spots, -1 for a couple of spots. Let's try 0. 0, you round 0 down, or divide 0 by 2 and you get 0, you round it down, it stays at 0. Okay. So for 1 divided by 2 is 1/2, round that down, you get 0 again. 2 divided by 2 is 1, round it down, it stays at 1. This goes to 1.5, round it down, you get 1 again. I'll fix that in a second. 4 divided by 2 is 2, round it down, it stays at 2. 5 divided by 2 is 2.5, round it down, it stays at 2, or goes to 2. And there you go. So start plotting these points, and I'm going to do it real fast. I'll pause it and put everything on there. And hopefully that doesn't seem too ridiculous. Alright, so there you go. I'm glad I paused it because it took me a second to do that, and it was probably not terribly interesting to watch. But there's our step function. It is kind of like the regular greatest integer function. Alright, but notice the steps are twice as wide. Okay, basically what happens is it takes twice as long to get to the next integer because you're chopping everything in half. Alright, maybe that's a helpful way to think of it. But round down to 0, round down to 0, round down to 0, boom, jump up to 1. Round down to 1, round down to 1, round down to 1, boom, jump up to 2. Okay? And it's taking longer to get to the next jump because you're dividing the x's by 2 every time. So it's taking twice as long. Alright, so that's definitely the hardest thing you have to, there's only one of those on the little worksheet in the review packet, but there you go.